Finding capacitance and reactance. So before we actually take some measurements, let's take a look at some equations here for a simple RC circuit. We have a 1 kilo ohm resistor and 0.1 microfarad capacitor, and our voltage source is 1.0 volts RMS, sine wave at 1 kilohertz. So to calculate the reactance, X sub C, that is given by 1 over 2 pi F times C, where F is frequency, C is the value of the capacitor. So here are the values, and once we calculate that out, we get 1,592 ohms. So that helps us determine the overall impedance of the circuit. So that's going to be Z, the impedance, is the square root of the resistor squared plus the reactance squared. So we do the substitutions and we get an impedance for this circuit at 1,880 ohms. So this is useful because now we can use this impedance to find the current in the circuit. We know the voltage source is 1 volt, so current equals voltage over the impedance, so that's going to be 1 volt divided by 1880 ohms. So the current in our circuit here is going to be roughly 0.53 milliamps. So now that we know that, we should be able to calculate the voltage across the resistor, because that's just Ohm's law. VR equals IR, so that's 0.53 milliamps times 1,000 ohms. So the voltage across the resistor should be about 0.53 volts. Let's take it one step further and derive the voltage across the capacitor. So using this equation where V squared equals VR squared plus VC squared, do the math and you get VC equals square root of V squared minus VR squared. Substitute the numbers and we get that VC should be roughly 0.85 volts. So here's our simple circuit on a breadboard, and what we've done is pretty much taken the oscilloscope probe and put it on the capacitor. The other one's on the voltage signal. So you can see here on our oscilloscope, the yellow is the source signal and the green is the voltage across the capacitor, which you can see is 90 degrees out of phase from the source. And if you take a measurement for the capacitor, we get about 0.81 volts, which corresponds to our prior calculation. Now we're going to switch the position of the capacitor and the resistor in the series circuit, and this is simply to make it easier to take a measurement across the resistor. So the oscilloscope probes are across the resistor as shown. So if we look at the oscilloscope, the yellow is still the voltage source and the green now represents the voltage across the resistor. So we're looking at a peak-to-peak value there, but if you take the RMS on the digital oscilloscope, we can actually get a measurement and it'll show RMS 500 millivolts, which is basically 0.5 volts. So here it is. That pretty much matches what we calculated earlier. Now if we were to use this, we can calculate the current in the system. So that would be 0.5 volts divided by the 1,000 ohm resistor. The current through the resistor has to be the same thing going through the entire circuit because it's a series circuit. So we get 0.5 milliamps. We can use this now after we've already calculated, or measured I should say, the voltage across the capacitor, which is 0.81 volts. We now have the current. Use that in this equation to get a reactance of 1,620 ohms, which is approximately what we had calculated earlier. Using this number, now we can use this formula. Capacitor equals 1 over 2 pi F XC. Make the substitutions and we get 0.0982 microfarads, which is roughly 0.1 microfarads. And that's what we started off with at the beginning of our calculations. So you can use these formulas to find capacitance and reactance. Just bear in mind the relationship between RMS and peak to peak. RMS equals peak to peak divided by 2 times 0.7071. Very often on analog oscilloscopes you're measuring peak to peak values and from there deriving the RMS value.